Okay, in this part, we want to talk about the differentials. Before we talk about the differentials, we want to look at one application for the tangent line, which is called the linear approximation. Sometimes it's called the tangent line approximation. Suppose we have a curve, okay, this is the curve, fy equals f of x, and we know the point here, this point is given by a and f of a. And we also can find this red line, which is the tangent line, y equals lx. And in the previous knowledge, okay, from the previous knowledge we have learned, we know if we know the function f of x, we know the point a f of a, then we can always find the tangent, the equation for the tangent line lx. So we can use the point slope form. So the Lx is equal to f prime of a times x minus a plus f of a. This is the point slope form. Okay. Then we give a name for this one. This one is called linear approximation of this fact f of x at x equals a. Sometimes it is called a linearization of this function f at x equals a. So now let's look at so why we want to study this linear approximation. That means when x is very close to a, for example here, very close to a, then you can see the black curve and the red curve are very close to each other. So in other words, instead of using the original function, we can use our tangent line at this part very close to a part. You can use this tangent line to approximate our original function. The reason is the tangent line is a straight line, which is a linear function. It's very easy to manipulate it. Okay, it's very easy to do the calculations, right? To do other things. So this is a very often technique in engineering. They always use a linearization to approximate, to replace the original function to do the further calculation when x is near a. So now let's look at this example. Okay, this example says find the linearization or linear approximation Lx of this function f of x equals 81 plus 2x squared to the negative 1/2 at x equals 0. So here a is equal to 0. So the linearization, we use the formula we have, right? The linearization Lx is given by f of prime of a times x minus a plus f of a. So if you plug in a equals 0, so you will have f prime of 0 times x minus 0 plus f of 0. Then the next thing you need to do the calculation, what is that and what is f0, right? So to evaluate f prime of 0, we need to calculate the derivative first. So here we need to use the chain rule because this is a composite function. The outside function is the power negative 1/2. So if you take the derivative of the negative 1/2 power, so then it will bring down the negative 1/2, then subtract 1, right, to get a new power. But here should be still, in the parentheses, should be still the inside function, 81 plus 2x squared. But also in the chain rule, we also need to multiply this one by the derivative of inside the function. So this is the chain rule. So then we do the calculation. At last, you will get this one. Then we need to plug in 0. The plugging 0, that means f prime of x, then plugging x equals 0. So that is, if you plug in 0, you will see it's equal to 0. Then what is f of 0? F of 0, you just replace x with 0 to here, right? X with 0. So you will have this one, which is equal to 1/9, 1/9. Then we plug in everything into the linearization, right? Then you will get Lx equals 1/9. So that means f of x, so this is the linearization or linear approximation. So what does this result mean? What does this result mean? This result means that f of x can be approximated by a constant function 1/9 when x is near 0. So you see, the original function is very complicated, right? Some negative power, and inside is some x, but the linearization is just a constant. It will simplify a lot of calculation for the further study, right? So the next we want to talk about the differentials.